SwayamPrabha. Digital India. Educated India.
Now, yesterday we had some interesting class on estimation. Estimation is the root of this inverse, because in any inverse problem in science and engineering, funda is we are trying to estimate something. This estimation could be thermal conductivity, density, or not thermal conductivity, emissivity, whatever, or boundary condition, latent heat, whatever be the stuff, heat transfer coefficient, and so on, mass transfer coefficient, okay, size of the tumor, size of the brain tumor, size of the breast tumor, and other properties, or a property of a star, okay, property of a star, the approximate composition of another star which you are observing, okay, using the telescope, whatever, and you're getting some information. All right. So, yesterday we discussed a lot of ideas concerning, okay, or pertaining to estimation. I gave you 2 problems which you're going to work out. I'll give some points for that assignment. I will tell you how many points and all that later on. But submit it off tomorrow. Then this I'm not going to. There could be a fun problem, okay, which I don't want to give it as an exercise. You can take it as a homework problem, and just like that Chicago tune-up problem. No? So one fun problem could be so. What can this be? What can this be? Huh?
Monkeys.
Okay, monkeys. Oh, who is that?
Me only, sir.
Okay. Okay. Something more decent. Well, not that monkeys are indecent. Okay.
Deer, sir, they are a bit more decent.
Then
Scorpions.
anything else? Huh?
Scorpions.
Why are you thinking about that? Scorpion. No. Okay. I had something else in mind.
Chairs.
Anybody else? Chairs. Classroom. Who's that? Classroom.
Professors.
Hey, professors you can get from internet, man. Professors is a okay. Professors is a trivial problem. Get from website. You may also tell me that classroom is a trivial problem. It is not so, because every department is organized as lab. For example, the heat transfer lab, we have a conference room and a seminar room which is used as a classroom. The IC engine has a 2 seminar rooms which can be used as a classroom. There are some mini auditoriums in some departments. There are some lecture hall. There is a CRC. There is a MSB. There is a HSB. There is a okay. So it is not so straightforward. Profs also, the other way of estimating would be what is the student-teacher ratio typically in an IIT? How many students are there? So this how many students are there has to be done BTech, MTech, MSc, MBA, MA, MS, PhD. Okay, and dual degree. So you have to find out and then how many teachers. So approximately if so many PhD students are there, each of them has a guide. How many students a professor can have? What is the normal average PhD number of PhD students the guide has? How many courses they are teaching? And what is so a prof teaches on an average, a prof teaches how many courses a year? 3 courses or 4 courses? What will be the class size? So how many courses? So there are various ways of approaching the problem. Is it okay? So this is a lot easier problem. Easier problem. This classroom is a tough thing. I went and asked the dean and all that and the academic section. I was shocked to know that nobody knows the answer to the question. Nobody actually, if you go even further, How many tables and chairs are there in IIT Madras? What is the answer to that question? How many tables or chairs are there in IIT Madras?
No one knows.
Huh?
No one knows.
God knows. God only knows. Okay. So the answer to the question is God only knows. They will say, sir, why, sir? If suppose you go and ask somebody, why, sir, you want some chair? I'll give chair. He said, I don't want chair. I want to know. Sir, no. If you don't have chair and table, if you want to change, you tell us, sir. We'll supply some chairs. That is the way they will work. Okay. So nobody actually knows. Nobody actually knows how many classrooms. Because IIT is vast, it is huge. So there are many things which are dumped also. Okay. Even in the heat transfer lab, I can pick up 10 chairs. They go to the backyard. All are in reasonable condition, but they have to be repaired to make it a usable condition. Or we got new chairs, and so that these chairs are all not used and all that. So we had some project to remove all the wastage in IIT Madras. We formed committees. I was in charge of the committee for removal of wastage from mechanical, like that process from other departments. So we asked some vendor to come and take it, and scrap value, we generated a few lakhs. More than that, we were able to declutter the space. Okay. Still a lot more, as because the institute started in 59. 62 years of junk has accumulated. So I think we have to do something about it. Okay. So this is as far as estimation. So you can think that many you can. So sometimes when I was a student, okay, when I was waiting at the bus stop and all that, I will see approximately out of 100 people, how many people are wearing shoes. Okay. So I will just try to do an estimate. And every 100 bikers, how many of them are wearing helmet? Okay. What is the helmet percentage? Then if this is the helmet percentage, how many helmets can they sell? Okay. And how much variety they are expecting. So how many different helmet manufacturers can be there in India? And how much will be the turnover? What could be the profit? If that is the profit, how many people can be employed in a helmet manufacturing company? How many people can we give employment? So this journey, all these journeys. So you have to basically you be aware. Whatever, don't always worry about grade, exam, this thing, or you get lost in YouTube, this thing, and somebody is forwarding something, some meme is coming or something. All right. So something, if you just look out, if you just look around, there are so many interesting phenomena, and then you do some thought experiments yourself, your awareness will increase. Then you will automatically become sharper and sharper. You will become very observant. Man has progressed so far because he has observed. All apples are always falling down, but somebody figured out that why is it doing so? Okay, so therefore we say that Newton did not invent the law of gravity. Law of gravity is already there. He discovered it. That means it was covered. Previously, it was covered. So the goal of knowledge is to discover or uncover the syllabus. A professor should not cover the syllabus. Is that okay? All right. Okay. Let's get started on. Okay. So I will formally introduce the course. So today also will be a soft class, but I will give you some flow chart and all that. So from Monday onwards, we start working on problems. So please bring calculator to all the classes, or if you have an online calculator, I mean, mobile phones all have, all the Android phones have that. So I don't know whether you get a sign. Is there an online scientific calculator also? Is there an app for that? Vehicles that pass through the main gate. Sai Pawan. Sai, what is that you want to find out, man? You want to find out vehicles that pass through main gate. Yeah, tell me. What did you have in mind?
Sir?
You wrote that, no?
Yes, sir.
What did you have in mind when you wrote that? Vehicles that pass through main gate.
I want to know.
But we can.
I want to know how many persons travel per day, so that we take some timing, so that we should allow all the outsiders do not pass through main gate all the time. We can specify.
Okay.
Because if it is open all the time,
so
some persons are coming, sir. That is becoming a big problem.
That is correct. What he's saying is all sorts of people are entering the campus at all the times. He says that we should restrict. So first we should know how many vehicles and then we should have on this. Okay. So please come ready with your calculators. So we will solve problems. Most of the classes there'll be an algorithm, there'll be a method. I will explain where it's useful as may be appropriate, and then we'll solve a problem. All right. So the inverse problem is basically the goal. The goal of any inverse problem. Okay. So that internet will be needed to get data. No means. What do you mean by that? I don't understand. So somebody is sending some message, so we'll respond to that later. So from the effects, we have to get the causes. Okay, this is the goal of a inverse problem. Okay, so patient. He comes with fever and body pain. Huh? Okay. Corona, flu, okay, some other infection. It can be anything else. It can be dengue. Okay. And God forbid, it can go all the way up to cancer. Correct? Now, you are presenting only with this, and you are thinking that doctor is God. Okay? He will just put the thermometer, he will just do this, that he will put and say, within 10 minutes, the doctor has to tell you, how is it possible? So he will compare, he will ask other questions. Are you having appetite? Are you having vomiting? Are you having diarrhea? Are you having nausea? Are you having a cold, cough, all that? Since how many days you are having this? This is the first time, or you got last month and again it is coming. Do you have any other problem? Do you have a prior history? Did you have a surgery? Or all this. So he's collecting data. He's getting priors. Okay. So he is collecting data, priors, clinical knowledge. So you will use all of this plus your symptom, and he will, if he suspects this, go to test. Go for test. Okay. If he suspects this, 3 days. 3 days medicine. If he says some other infection, blood test. If he suspect, and are there a lot of mosquitoes in the hostel? Did you get bitten? Were you playing out in the open? Where did you go out in the evening hours? Were you always there outside in the evening hours when were you bitten by mosquitoes? He will ask all this. Okay. Or do you have a lot of stomach pain? Your stomach becoming heavy. Okay. Did you eat something in Velachery? So he will ask all this. Then, so this is a classic inverse problem. Doctors are all the time dealing with inverse problem. Now, same patient, okay, vaccination, body pain, fever. This is a direct correlation. So if you have a brother or a sister or a cousin who got married, who was a small infant, or you remember or you have a sibling, some years back, you remember your parents used to take them to the pediatrician. You give the vaccine, next to 2 days, the baby will be crying. In that case, unless the baby is healthy, you will not vaccinate. So after vaccination, immediately that night itself, fever comes. So this body pain and fever in this case, it is it's more or less like a direct problem. There is nothing to, because So this is the cause. Vaccination is the cause. Fever is the effect. And it is not an inverse problem because for this fever, again, you will not go to the doctor because you know what the cause is. Okay. If the cause is not known, and you also know in 2 days this problem will be solved. First, there will be swelling and all that. Baby will keep on crying. It will be very irritable because the vaccine is working. So after 2-3 days, it will settle down. So it is the same body pain and fever. If you know it, it is a different. It is not an inverse problem. If you don't know the cause, it is an inverse problem because you have to get all right. In this case, you will get all right. Okay. So that is the. So this is some nice example which is not connected to heat transfer. Okay. So this is as far as this is concerned. Now what? Okay. So causes. Normally we call causes as X in this course. The effects Y. Okay. This is called forward problem. Sometimes I may use this interchangeably with direct problem. If you are an MTech student or a BTech student, the whole of your MTech and BTech life, primary school, middle school, high school, higher secondary, BTech, MTech, all the courses, you are solving only forward model. You are always where all the professors, the whole knowledge is based on if this is the cause, that is the effect. This is the cause, that is the effect. The body is in motion. This thing, Newton's first law, second law, third law. Body is heated. Body is cooled. Thermodynamics, heat transfer. Body is stressed. Stress analysis. Okay. Okay. Water is seeping. Okay. Water is seeping underground. Okay. So it is some groundwater engineering. Water is overflowing. Okay. Hydrology. Okay. Water is getting evaporated, coming as rain, causing flooding. Atmospheric science, weather prediction, climate change. Okay. So mechanical energy is converted to electrical energy. I want to transport it electrical technology. Okay. So microprocessors, building up the microprocessor and making up a computer or some, okay, or a workstation. Okay. In all these cases, if you do these things, you will get this. So most of the times you are dealing only with direct problems. But real life, apart from direct, real life often may throw up challenges of an inverse problem. A car mechanic is all the time dealing with inverse problem. You'll go and say, from yesterday it is rattling, the car is giving a lot of noise. There could be 1,000 reasons for a vibration or a noise in a car. Okay. So you will say, pickup is not good in the scooter. So then he will use his fundas, prior knowledge and all that. He will say, I have to see. He has to fuel injection pump, the cable and this thing, and whether there is any leak. Otherwise, if we can't solve that, they have to open the engine and do all that. Okay. So life, even from a mechanic, a doctor and all that, even if you are in a power plant, suddenly the operational efficiency of the plant decreases. The AC plant is not working properly. So all your bookish knowledge of forward model will not help. The forward model will help you better than others. Okay. So you know the correlation between the effect and the cause, but you will have to figure out the right causes. Okay. Therefore, the assumption is if you are good in the forward model and if you've got a lot of common sense, you've got experience, you can combine all the common sense experience and your good knowledge of forward model to solve the inverse problem. Life will most likely present a lot of inverse problems to you. Okay. What is the inverse problem? The inverse problem is effect Y causes. Don't think it is this Y is elementary. This Y could be Y1, Y2 up to Yn. This Y is invariably a vector. Okay. This X is also a data vector. This could be X1, X2 up to Xn. What could it mean in thermal engineering? This could be rho, Cp, K, epsilon, heat transfer coefficient. It could be anything. Of course, there is no inverse problem which will get all this together. If it is, if we devise something which will give everything in one stroke, then we should get Nobel Prize, right? So there is no inverse model which will give all of this. I'm just writing it as a laundry list. Okay. So invariably, this is an F vector. This is also a vector. So multiple causes can cause the same effect, and the effects are usually, for example, if there is a slab, I am having measurement at 5 places, T1 to T5. Okay. Suppose it is the form of a cuboid. I can have measurement here of temperature, measurement here, measurement. So temperature could be 20, or I take a thermo infrared camera and capture this radiation, and using something called calibration. From this calibration, I know what the temperature is. Then why 5, 10, 50? I can have 500,000, 2,000. Let's go even better. I can take some sheet. Okay, there is some plastic. You say, okay, this is some plastic sheet. Huh? This is some plastic sheet. Okay, some my stuff is there. That's okay. This plastic sheet. There are sheets available which you can stick onto this. If it is heated, it is made of what is called thermochromic liquid crystal, TLC. Suraj is doing PhD on that. Thermochromic liquid crystal. The funda of that crystal is it changes color depending on the temperature. Then you capture it on a high-speed camera, save it, then use digital image processing. Now, each color represents some temperature. So what is the correlation between the color and temperature? First, you will take some sample. You make a copper block or some dummy sample. You heat it, and using thermocouple or some other method, you first measure the temperatures at various places. At that time, you take color picture and find out green color is 44, blue color is this much. So there is a correlation between color, and you can quantify this as hue, saturation, intensity, or red, blue, green, RBG color, or hue, saturation, HSI. Okay, this is what is done in digital photography. And then this is called calibration. Then in future, once you do that, you know that this color represents this temperature, the other color represents the other temperature. So whenever you get a color plot using DIP, digital image processing, you can directly get the temperatures. This is an optical method of measuring temperature. Don't think temperature means doctor putting the thermometer in the patient's mouth. That is starting. We have resistance thermometer. We've got so many other PT100, thermocouple, thermal infrared thermometry. Infrared, you're seeing, corona, everybody using that's all infrared. Okay, wherever you go, they are checking your temperature. That's based on infrared emission. Okay, so temperature could be many things. It could be many temperatures, and there could be many causes. From the many effects, can you please tell the correct cause? That is the goal. This is basically the inverse problem. This is a graphical depiction of an inverse problem. In this case, the most important point you have to deal with is called is basically the curse of dimensionality. Okay, the curse of dimension. Few data to figure out multiple clauses. Are you getting this point? So this is a fundamental problem. There are only few temperatures. With that, you want to write a full story about that slab. Not possible. That is a curse of dimensionality. It's particularly true in remote sensing and all that. Okay. For example, so this is the ocean. Okay. Let's say this is the ocean. This is the surface. Okay. So this is the atmosphere. Okay. So this is, let's say, this ocean surface is having some emissivity and temperature. Now, consider that you are having a infrared imager or sounder. That infrared imager or sounder will pick up the radiation coming from the Earth, from the ocean surface. Okay, you can make this say go in a satellite and you can measure different positions, or you can make it as a geostationary orbit where it will constantly watch at only one position. You can choose INSAT 3D will always watch India. Okay, if it is a polar orbit, then it will rotate. So this geostationary orbit, you take it all the way up to 36,000 kilometers and put it there. Okay, that is why we use what is called the GSLV vehicle. The GSLV vehicle is several stages, so it will just finally push it at 36,000 kilometers. At 36,000 kilometers, there is no friction, and then once you put it there, perpetually it will keep rotating. Then once you give the initial this thing, it will maintain its orbit. Okay, there is no problem there. Okay, so of course there is some battery life and this thing. So for that, what you can do is you can have a solar panel; it will recharge itself. So this is all satellite design, antenna design, all this is separate. So India is a leader in all this now. Okay, now the question is different here. Now I'm measuring the radiation is coming on the top, but this is the effect. This radiation can be measured in some frequencies called so many hertz. I can have measure in megahertz, gigahertz, whatever. There are some channels. These channels have to be carefully chosen based on the characteristics of the atmosphere. What do you mean the characteristics of the atmosphere? It is not a dry atmosphere. At least up to the first 18 kilometers, you got water vapor. Sometimes there are clouds. You can have ice. You can have water. You can have snow. Whatever, depending on whether you are in a tropical country or you are in temperate climates, Canada, Denmark, Greenland, and so on. Okay. So suppose you divide the atmosphere into various, for your understanding, you divide it into various levels, and then you say that there is a T1, T2, T3, T4, up to, let's say you are dividing the atmosphere into 96 levels. Okay. And then each of these levels has a temperature and a humidity, omega 1, omega 2. Now, there could be 96. Most importantly, there could be, what is more important in this case, which causes the radiation at the top, basically these 96 temperatures, these 96 humidities, plus the emissivity of the surface. The emissivity of the surface for a still water, it could be different. If there is a cyclone which is going on, the ocean will be very turbulent. So whatever is coming from the ocean, which is seen by the instrument at the top of the atmosphere, will be different. So let us say it has got some 198 causes. Now, how much can I design? I can design this based on some, these are called channels, right? That's what is called the satellite channel. Okay. The satellite channel can be 8 channel, 10 channel. The INSAT 3D has got 18 channels. Okay. So you've got 18 values of the radiation intensity. Okay. 18 effects. Now you honestly tell me, isn't it asking for too much? From 18 effects, you want to understand or predict 198 causes. This is the curse of dimensionality, because there could be multiple combinations of temperature and humidity. So all this is because some radiation is happening here. So that is radiation heat transfer. Okay, in a medium which is participating, which you may or may not have studied. I don't know, depending on where you studied and all. Even in IIT, we don't teach that. For participating medium, it's little advanced. BTech, we don't teach. Okay. There could be various combinations. Some combinations can be silly. We can leave it out. Some combination will tell you there is lot of ice here and lot of water vapor here, which is against physics. Ice could be only at the higher level. Okay, so if you have multiple combinations, some combinations are infeasible, you cut them. But even then, the feasible combinations can be very high. From this, you turn around and tell me what will be the state of the atmosphere. The goal is to get the state of the atmosphere. This is called remote sensing of the atmosphere, remote sensing of the environment, remote sensing of the environment. Otherwise, we have to launch balloons and get this data, which is very expensive, time consuming. So this is satellite meteorology. This field is called satellite meteorology. In this case, there can be hajar causes and few effects, and you want a greedy solution. I will measure only at 18 frequencies. You want 198 causes, means it is very tough for the scientists. it is very tough for the algorithm designer. So we have to do a lot of things. So you have to separate the signal from the noise. So this is a huge activity by itself. Now we have come to a stage where you've got hyperspectral sounders. India is also in the game. We are having channels with 3,000 channels. So we'll beat this stupid game by just measuring at 3,000 frequencies, and then from that, if you get 198 passes. So always information flow in compression is very good. I have a lot of measurements. I have a lot of data about the patient. Patient is coming with fever, body pain. I have done stool examination, urine test, blood test, chest X-ray, this thing, CT scan, MRI scan. I have all the data with me. Then it is easier for me to find out what the cause is, because I will just kill with data. That's what we say. You kill the problem with data. So, but killing the problem with data means so much money. Okay, here if you put a 3,000 channel, it costs money, and if that takes, it will be hundreds of crores. It will be hundreds of crores, and there should be a reasonable scientific output based on that. Okay, so those are all considerations the government has to take. Now, you can floor something with a lot of data, but this is called big data. This is called mass. This is called data analytics, big data. So big data is there not only in finance and stock market. Big data is there in weather prediction. Big data is there in atmospheric science. Okay, big data may also come if you are in a company where where heat exchangers are made. All the heat exchangers are working. So every day, suppose you have a chip and you get the data onto the manufacturer, you can study the performance of the heat exchanger, and then you can come out with new jugaad design based on this. For example, every time an Airbus plane or a Boeing plane flies, Airbus and Boeing automatically get the data about the engine and this thing about, you know this? I don't know how many of you are aware. So every plane which is flying anywhere in the world, the manufacturer will get the data of the performance data. The engine is stalling, the power is this thing, or there is a crash. If there is a crash also, not only the safety regulator of that particular country, the manufacturer also gets some data, what is happening and what are the protocols. They'll give you all the measurements, temperature, pressure, this thing, all over, inside temperature, cabin pressure, all those details, outside conditions, storm, this thing, all those things are available. Okay, so inverse problems will become more and more popular, more and more in demand. If you are a guy who knows inverse, you can do a lot of things because you can deal with big data, lot of data. And there are a lot of subjects, not only in the conventional business. So they originally started with data analytics. What is the data analytics? Amazon, so many people are buying so many things. So somebody has to write a program, study the consumer behavior. So you just split it. South Indian, Tamil Nadu people, what are they buying? Rajasthan people, what are they buying? And somebody is working, right? So suppose you buy a shoe, you're looking for a shoe from I look for some shoe or something. I have a fancy for automobiles, and so I look at what is the next car which is coming or something, a two-wheeler. If you search, how come whenever you go to any other computer with your Gmail, it says Balaji, last time you're looking for this, last time you're looking for. So even if you want to buy for T-shirt or something, or you just say that Bluetooth, this one I got Sennheiser. No, it will ask, okay, new Sennheiser model has come. It will not allow you to live in peace. So somebody is working on this big data. Somebody is studying consumer behavior. But man is crazy, right? So just because based on his past data, you cannot say that he will behave only according to this. But be that as it may, it is a miracle that with so many people clicking their mouses and this thing and so many different places for different things, something is working in the background and somebody knows exactly what is your spending pattern. If you bought some kind of book, it will say some new book which is in this field has come, we want to buy. Some arbit, it will say some, and it is incredible. Okay, so in 2016, I was a visiting professor in IIT Bangalore. Okay, I had a lot of students. My family was in quarters. I mean, so Monday to Friday, I will be in Bangalore. Friday evening, I'll take a flight and then come to Chennai. Saturday, Sunday, I'll meet the research scholars, family will do. And Monday morning, 8 o'clock flight, I will go back. Okay, and I used to teach atmospheric science in Institute of Science. Then after 3 or 4 days, after 3 or 4 Mondays, okay, when I switch on the Google map, it will say, do you want to it won't even ask IAC guest house. It directly tells me IAC guest house 47 minutes. So it is not only incredible, it is scary, right? There is no privacy. Yeah, I didn't tell. Why? I don't want to go to IIT today. I may go to some other place. But he says, Balaji, every Monday you're doing this. I know about you. You will go only to this place. So you must know that with big data, people are continuously watching you. All right. So this cell phone, you think it is immense. Cell phone is a trap. Cell phone is worse than CBI or FBI. Okay. Cell phone on the internet. Cell phone with location on. Cell phone with internet on is like an invitation to destroy your privacy. Okay. So this big data is not there only in business. So we are trying to. So we don't want to be left out. So the idea of starting this course is basically why always forward to analysis. Let us work. Let us build up on the idea of estimation. And it's not like helter-skelter estimation. Estimation based on solid principles of mathematics, statistics, probability, and let's apply it on a domain, because the domain which I know is heat transfer. That's why we started this course in 2019. But the idea is, please, whether you do well or not, you're not very much interested or not in the subject of heat transfer, it doesn't matter. Just get the key ideas in this course, okay? And then wherever you are, even in life, I hope that because all the time we are solving inverse problems, we'll be able to, we will solve problems better, because this is a different way of looking at problems. Okay, inverse. Now let's come to inverse heat transfer. Okay, what is the motivation for this subject? So this is the broad overview. Now, what is the motivation for doing this subject? Okay, now it's quite recent. So less than 40, 50 years old. That's all. So it is less than 40, 50 years old. Okay. Where is the motivation? So the mechanical, metallurgy, meta, aero, CH, in all this, industries and establishments. Each of this, there's a chemical reactor, fouling is taking place. I want to understand. I want to do some troubleshooting. In mechanical, there are so many problems, right? There's so many. So I've got a data center or a computer center which is working. So all the things are getting heated up. I want to investigate. Can I, without investing too much money, can I reposition the server? Can I revert the ducting? Something, can I solve the problem so that all the systems are under safe operating temperature? Can I provide extra chill air, or I can have chilled water, and chilled water comes in contact with air and that will gives chilled air? Can I have floor from the floor? That's what it's doing in computer center. From the floor, I want chilled air. That is one thing. And then there are also this floor mounted. Okay, there's floor mounted air conditioning packs, which you must have seen in some hotels and all that. So that can you target on this supercomputers or those servers which are heavily, for example, the internet server or some other server or the supercomputer where everybody is trying to do calculation. So this there we have to do. It is not basically you're not solving a CFD problem, going to COMSOL and Fluent and solving and all. Here you've got a lot of data of something which is working. So it requires a different kind of a ball game. Yeah, simply okay, go to this thing and meshing this thing, solving the problem and getting a result and publishing a paper. That's all right. Or publishing a thesis. In this case, you have to troubleshoot. Okay, so there are problems in met. Aero, there are plenty of problems. Aero, there are plenty of problems. Okay, I want to investigate the health of an aircraft. Okay, I want to investigate the health of an aircraft by doing non-destructive testing. Okay, and also I have got data from all the Boeing Airbus planes, and suddenly everybody complaining that the first 20 minutes the air conditioning is not good. People are sweaty, people are uncomfortable, and then how do they distribute the air? So this air conditioning problem is a big deal because the relative humidity is very low in an aircraft. Okay, so there is some heat transfer there in metallurgy. Also, there's so many heat treatment processes and so on. some process is not working properly. So properly in all these cases, there is a motivation to study the inverse problem. Okay. Not only engineers, so fundamentally, okay, mathematicians, physicists, statistician. Also interested. They are also interested in general field of this thing. Why? Mathematicians are interested in developing new techniques. Statistician, okay, try new priors, new statistical models, which can be applied to an inverse problem. Monte Carlo simulation, Monte Carlo stop sampling, Metropolis Hastings sampling, Gibbs sampling, importance sampling, and something called, there is a heavy tail distribution. Let us try with non-Gaussian distribution to capture why there is a big Bombay rain, why Kerala got heavy rain in 2018 and 2019. If you model everything using Gaussian, plus or minus 3 sigma, 99% of the points are contained. But these are all outliers. How to capture outliers? What sort of distribution? I have to use a Weibull distribution or some other distribution. Extreme value statistics. So I want to study that. So these are all, if you work deep in this area, big possibility that somebody can end up with a Nobel Prize also, okay, or a Fields Medal or something. So statisticians are also interested. Okay, physicists. Okay, particularly they were interested in, for example, astrophysics. Right? So they want to study stellar structures. What is a stellar structure? A stellar structure is the structure of a star. How do you study the structure of a star? You can't go to the star and measure. So what you do is you take an emission spectroscopy or you take an absorption spectroscopy and using some sophisticated instruments and get the data. Then you have some model about the composition of the star, and then you do some calculation, radiation calculation or whatever, and then predict the absorption spectra or the emission spectra. That will not match with your experiment. So keep on changing the model till it agrees. Then you will get what composition of gases in the star is likely to be the culprit for causing this. So this is a classic inverse problem. Astrophysicists are all the time solving inverse problem. Is that okay? So as far as heat transfer is, these are the general drivers of inverse research. Okay. Of course, now you can say behavior, online, this thing, and big data and business, data analytics, and all that. Is it okay? So I'm talking about this inverse in science and engineering. Okay. Heat transfer. The motivation was, yesterday I told you, the re-entry vehicle. Okay, I drew it here. Okay, so the vehicle is going like this. The vehicle is going like this. So this is the atmosphere. The vehicle is going at a velocity of u. Okay, so this is something inside. Lot of stuff is there in the vehicle. Okay, now so this is z, and this is r. Here r equal to r naught. So q of r naught z t is what you want to know. As the vehicle is going on the surface at various values of z, so you can probably take Z equal to 0 here, the origin is here, axial coordinate. At Q, at R equal to R naught and Z at some particular time, what is this? You cannot directly measure. If you put a heat flux gauge, it will be destroyed because it is terrific heating. Why is the terrific heating? Because mv square by 2 is converted to Cp delta T. What is mv square? Mv square by 2 can be terrific. This V can be Mach number is about 6.5. Mach number can be around 6.5 for a hypersonic vehicle. Okay, so V could be thousands of kilometers per second. Let's say for the argument's sake, it's 4.3, 4,000 kilometer per second. It's 4 into 10 to the power of 6 meter per second. mv square by 2, multiply the vehicle weight. mv square by 2 is equal to Cp into delta T. Cp of that material, if you take, what will be the delta T of this material? So it will be that mv square will be everything, the load comes onto the weight, comes onto the body. So now the challenge is, can you tell what this is? It is not an easy problem to solve. So what they try to do was, they take some measurements. So T of R, Z and T, okay, measure. Measure T of R, Z at certain finite values of R, certain values of Z at certain points in time. Have an unsteady heat conduction problem. Solve it with some assumed values of the function estimation. So this is the estimation problem. It is not estimation of Maruti service center or number of monkeys or scorpions. It is serious estimation. Basically is estimation of the heat flux on the surface, which varies with time, which also varies with distance. So it is not an easy problem to solve. Many daredevils gave up. Professor Beck was the first person to solve it from East Lansing, Michigan State. Okay, he's still there, retired, about maybe 90 years old. Okay, so he's the founding father of inverse heat transfer. So you solve the conduction problem, and then with these measurements, what you do is basically fundamentally, I'll stop in a minute. Assume some distribution of Q of R naught ZT, solve the heat transfer, heat conduction problem, okay, and predict the value of PR of PR ZT and compare it with those values in which measurements are available. They won't agree because this is a guess value. Now change the guess value. Keep on changing the guess value till the difference between these two, either in a least square sense or something, is minimized. So there should be a proposal to find out what is the parameter. There is a minimization you are doing. So you're treating it as a minimization problem. Therefore, all the principles of optimization are going to come here, because the parameter estimation problem is treated as an optimization problem of minimizing the difference between the simulation and the experiment. And then, so there is an optimization, minimization. That is one proposal here. Then, are there some prior beliefs? How do you quantify their beliefs and put it in the system? And more importantly, is there a helter-skelter approach in choosing what distribution of Q you will have to use? So all this will not come from a knowledge of the forward model. You have to go through the subject of inverse, whatever be the field. There is a scientific way of generating samples. There is a scientific way of finding out what to minimize. There is a scientific way of prioritizing and quantifying your beliefs, so that finally you get a meaningful outcome, because this thing has to work. Otherwise, if it vaporizes into thin air, then the mission will be a failure. Okay. So any doubts so far?